Hey guys, welcome to the video where today we'll be talking about isotopes. Isotopes form when two or more elements contain an equal amount of protons, but they differ in the number of neutrons in their nucleus. So with this difference, they also have a difference in their relative mass, but they do share the same chemical properties. So down below, I do have this example where I have three Spalding balls, right? And these are going to represent our elements or isotopes, right? So again, all three of these are the same. They're all Spalding. However, they differ in their size and the amount of things that they can do or they're used for. So the first Spalding ball, we have the NBA Varsity. We can see here that it's tough and it's the smallest of the three, right? Next, we have the NBA Tac Soft. It's better for shooting. It's the medium sized, right? And then we have the Spalding TF1000. It has grip. What else does it have? Microfiber composite. It's a great practice ball and it's a great in-game ball, and it's relatively bigger than the other two Spalding balls that are there, right? So this gives a perfect example of how isotopes work. Again, they are the same element. They have the same number of protons. However, they differ in the amount of neutrons. Therefore, they have different masses, right? However, same chemical property. So if we go on to our right, we can see a more practical example here where we have carbon 12, carbon 13, and carbon 14, right? And all of these isotopes are naturally occurring in nature, right? But the one that we're really used to is carbon 12, right? As seen as the periodic table here, we can see carbon. And in the last video, we did talk about the atomic number, the atomic mass. And we can see that carbon's atomic number is 6, meaning it holds 6 electrons and 6 protons. The atomic mass here is 12. And if we were to subtract that 12 from 6, we get 6. Therefore, there is 6 neutrons. So this again is carbon 12. We also want to highlight that the number of protons and neutrons give it its mass. So again, we have 6 protons and 6 neutrons, and that's what gives us that carbon 12, the mass number. So now if we look onto our right, we have carbon 13, and ooh, this guy's a little bit heavier, right? It has 6 protons, right? All these isotopes have 6 protons. This carbon 13 has 6 protons and 7 neutrons, right? So that, if we add those up, it gives us that 13, carbon 13, real bougie, right? And then we have the big guy right here, the big guy. This guy's huge. We have carbon 14, right? He wants to be exclusive, carbon 14. If we add up the protons and neutrons, we get that 14. So again, here we see carbon 12, carbon 13, and carbon 14, right? All, again, the same element. They're all carbon. However, they differ in the amount of neutrons in their nucleus, right? So another thing I want to highlight are these percentages here that we see, right? And carbon 12, again, all of these carbons occur naturally. However, some occur more than others, of course. Our regular carbon that we're used to 98.9% of the time. However, if we look at carbon 13 and carbon 14, carbon 13 occurs 1.1%, and then carbon occurs less than 0.1%. So it's very rare to find carbon in these other two forms. However, it spontaneously does happen, correct? So now the next thing I want to go into is kind of stability. If we just zoom in right down to the bottom, we can see our best friend carbon 12, the one we're used to. It is very stable, right? And in the last video, I mentioned how there has to be a proportionate amount or a ratio of protons and neutrons in the nucleus for stability, right? So we know that there's 6 protons, and 6 neutrons in this nucleus of carbon 12, right? Now in carbon 13, there's 6 protons and 7 neutrons, right? However, it's still stable. We're still safe here. Then you have carbon 14, this big tough guy. It has 6 protons and then it has 8 neutrons, right? As seen right up here, 8 neutrons, right? So let's zoom back down here. It wants to be tough. It has so much neutrons. So what happens here? It's holding too much. If you guys think about someone trying to carry too much groceries into the home, or that tough guy, they want to carry so much books, and it's piled up to the ceiling. It's like, dude, just get rid of some. You want to be stable. You're unstable right now. And this is kind of what happens with carbon-14, right? It's very unstable. So what happens? Radioactive decay is what happens, right? Because they need to, when I say they, I mean the nucleus, the atom, it needs to become stable. So again, what happens is radioactive decay. And I'm going to make another video going into more detail about this because I think this is a very important topic. But for the sake of this video and just keeping it real basic, right, and very simple for people to understand, we have something that's released. And the particles that are released are called alpha, beta, and gamma particles, right? Beta particles, we see that an electron is released, and in alpha particles, we see that a whole different element can be formed. And in gamma rays, we can see not much has changed, and these are actually where it's very detrimental and very dangerous to deal with, right? And then of course down here we have an additional example where we have this unstable carbon-14, and again, when it's very unstable, it wants to become stable. So radioactive decay occurs, and an electron is pushed out and it becomes a whole different element. That carbon-14 turns into nitrogen-14. Again, guys, there will be a more in-depth video going over this, just so there's no confusion, right? Because I just prefer to do a separate video just to focus on that. And if we go into our last slide here, we can get even more practical. How do we use this into our regular lives, right? We know that these radioactive isotopes, I'm sorry, I can't talk today. These radioactive actitopes, oh my God. These radioactive isotopes, you know what it is? Radioactive. When I say active, I want to say active again. These radioactive isotopes are used as tracers in important diagnostic tools in medicine, right? So one example I like to use is kidney disorders, right? The patient is given small doses of substances containing radioactive isotopes, and then they're able to measure the amount of tracers excreted in their urine, right? These are radioactive isotopes we're putting into our bodies. So not all of them are necessarily dangerous, right? This is something that is like very important also in PET scans, right? To monitor chemical processes and to actually look into cancerous growths, right? Another example we have here is in carbon dating, right? And we know that a lot of researchers, they use it to measure the radioactivity in fossils. And this is their way of dating some of the past lives of that fossil, seeing how long it's been there, its age, and all sorts of things. And then to our left, we have a cyclotron, right? Isotopes do occur naturally. However, they can be made artificially by bombarding a stable nucleus with charged particles via an accelerator. And a lot of times we know about atomic bombs and how they're made with these very heavy elements and artificially made. So not only do isotopes occur naturally, but they can also be artificially made in these labs and these crazy physics underground tunnels and stuff of that nature. So again, isotopes are very important. Also, they can be very deadly and detrimental. And just a quick overview or recap again, we just want to say that, remember, isotopes are the same element, same number of protons, differ in neutrons, therefore they have a different relative mass. That difference in mass makes some of them very unstable, and these isotopes or elements, they need to be stable, so they go through radioactive decay. So that concludes the video, guys. I hope it helped. We'll go more in depth into this, and tell me, is there any more chemistry stuff that you guys want to talk about? Because what I'm doing is I'm trying to create a whole plan where I go from the beginning of biology all the way down to organic chemistry and further. All right, guys? So take it easy. Peace, guys.